All right, so let's move on to thermal energy generation. It's kind of our new topic for today. All right, so thermal generation, I guess if you've taken thermodynamics, you should immediately be uncomfortable with me saying that there's such a thing as thermal generation, right? There is no situation where energy is just created out of nothing, right? Maybe the Big Bang qualifies in some way, but I don't know. Or you can't just create energy out of nothing. So what do I mean when I say thermal generation? Well, it's actually just conversion of one form of energy into heat. So let's come up with examples. Maybe this will help. So thermal energy, maybe what are some examples where you can have thermal generation, this conversion of one form to another? Any? Combustion. All right, so combustion just more generally is like a chemical energy transformation. Any others?
Joule heating.
Joule heating, so like electrical resistance. Nuclear. Nuclear, see if I have any other ones here. What about absorbed radiation, which is sort of like nuclear, but think you have like a pane of glass and it's absorbing energy that's passing through it. Right, so these are all possible examples of thermal energy conversion from one form to another. But when we're talking about heat transfer, like this is a class where we just care about heat has been created, now what happens to it, right? That the source is maybe not so important. It's interesting to look at specific examples. But now that we have thermal energy in a body, now we have to think about where it's going and what the temperature implications are. So when you talk about thermal generation, it is just conversion of energy from one form to another. Another thing to note is that it's almost always what we'll call a volumetric phenomenon. All right, and by that I mean you're producing some power in, say, joules per second, which is a watt. You're producing power, and it's happening per unit volume. So your units are always going to be watts per meter cubed when you're talking about generation. One thing that's important is, okay, you do a controlled volume analysis. Thermal generation can appear in your control volume. If you're doing a surface energy balance, that is like you're looking at heat flowing across an infinitely small surface, can you have generation there? No, because there's no volume available for actually generating that heat. So anytime you're doing a surface energy balance, make sure you're not including generation in that, okay? Okay, so that's generation. I think what we'll do is let's jump right into an example. And this example will help us maybe understand how you go about deriving analytical solutions for problems with thermal energy generation. All right, so I've got, let's see if I still have that up. Okay, so how many of you guys have seen this? We all live in Wisconsin now, right? So we know what this is. Hay bales, right? Hay bales out at some person's farm, and they roll them up, and then they cover them in plastic and feed them to the cows or whatever, right? So we have a situation there where, sorry, I had to show you because my image gets inverted. It's very ominous looking hay bales. So you have a situation where you have this organic matter, right? You roll it up into a long cylinder and you let it sit there. And that organic matter is still, it's alive, right, when you do that. So it's still generating heat. It turns out if you make the hay bale too large, the thing will actually start on fire. Right? And there are examples probably almost every year of barns that burn down because people don't store hay properly and it gets too hot. So farmers have maybe rules of thumb. They say don't make it too big. Don't harvest when there's a certain amount of moisture. But as thermal engineers, we can sit there and say, all right, well, tell me a little bit about the problem and I'll tell you what you can do, right? So let's go through and do this example where we have thermal generation in this application. We're given some problem information. We know, okay, a bale of hay is going to start on fire if it reaches 170 degrees Fahrenheit. It's at this stage in its decomposition, it is generating 2 watts per meter cubed, which is not a lot, right? 2 watts is a small amount per meter cubed of hay. And then we have some properties of the plastic, of the bale, and then the ambient conditions. So let's see. Let's go through this and start by doing what we're always going to do, which is do a control volume analysis in the area that we're going to model. So we're going to model the temperature distribution inside the hay, okay, only. All right, so let's draw a control volume. I'm going to just pick a slice, differentially small slice inside the cylinder. And let's do a control volume analysis on that. So let's see, where am I? So what we have, this position here is going to be, we'll call that R. Coming into the control volume, I have Q dot at R. Leaving the control volume, I have Q dot at R plus dr, which implies that this distance here is dr. And unlike previous problems that we've done, we have thermal generation occurring in here. So we'll say that there's some G dot that's associated with this control volume. All right, so I think I've accounted for everything. It's a steady state problem, so there's no DUDT. There's no other place that he could be going. Right? It's circumferentially symmetric, so there's no reason for heat to flow in the circumferential direction. We're just modeling it as a 1D in radius. So I think we're good to go. So let's put all this stuff in an energy balance and then write it all out. So energy balance is going to say what's coming in is Q dot at R. What is being generated is G dot. And then what's going out is equal to Q dot at R plus dr. Right? One point I guess I haven't made before is this R plus dr thing is just a subscript, right? It's not saying Q dot at R plus dr. It's Q dot subscript R plus dr. Okay, it's just we're denoting that's where that is occurring. Okay, so let's expand this out. So we have now we're going to say that this term can be expanded out to Q dot R plus dQ dot R dr times dr. We're just using our definition of the derivative. And then sub that back in, and we end up with Q dot R plus G dot is equal to that, which is Q dot R plus dQ dot R dr dr. All right, so at this point now, we want some expression for G dot. All right, so G dot, we've said that there's a generation occurring. That generation is in units of watts because everything else is in units of watts. So we need a way to go from the specific information we have here, which is G dot triple prime, our volumetric generation, to an actual watts. So let's write an expression for G dot. That is going to be, so G dot is equal to the volume of that little shell. So that's going to be 2 pi r times dr times L times G dot triple prime. So you see where that came from? You have the shell circumference, the differential thickness, dr, the length into the page, and then G dot triple prime. All right, so we have the G dot. We can substitute that in as well. And our expression, let's see. Yeah, let's do this way. So first of all, I can cancel out the Q dot R. I don't need to bring that along. Substitute in G dot, and I end up with an expression that looks something like this. 2 pi r times L times dr times G dot triple prime is equal to dQ dot R dr times dr. All right. I have a dr appearing on both the left and the right-hand side, so I can cancel that out. So dr goes away, and I'm left with, let's see, dQ dot R dr is equal to 2 pi r L times G dot triple prime. Okay, so this is our ordinary differential equation for Q dot for this problem. And it's a little different from last time, right? Last time we had dq dr is equal to 0. Now we have dq dr is equal to something. And again, like physically that makes sense because we're saying the rate of change of heat transferred is not 0, right? As you move out in radius, you're accumulating additional generated heat that now you have to conduct. So there's a non-zero rate of heat transfer change as a function of radius. Okay? All right, so let's keep moving on this, and there's the expression we just derived at the top. So let's figure out how to get this in terms of temperature, solve this ODE for temperature. All right, the first thing we need to do then is introduce a rate equation for Fourier's law to bring temperature into play. So let's say Q dot R is equal to Fourier's law, which is minus K 2 pi R times L times dt dr. This is just Fourier's law for a cylindrical geometry. Okay, we can substitute this whole thing in up here, and we end up with ddr of minus K 2 pi RL dt dr is equal to 2 pi RL g dot triple prime. All right. Again, I can cancel some stuff out, right? I can get rid of the 2 pi. That goes away. I can get rid of the L. That goes away. I can take this minus K and divide out both sides so that I get the constants out of there. And doing that, then we end up with the equation ddr r dt dr is equal to minus r g dot triple prime over K. Okay. So now we have our ODE in terms of temperature. And again, it's different from before. We have something over here where we didn't previously, right? In the case without generation. This, by the way, is, so if we start labeling our ODEs, what we had before was we had an equation where we have a differential or some function of temperature on this side and then 0, like nothing over here on this side. That's called a homogeneous ODE or homogeneous PDE. Anytime you have everything as a function of temperature on, say, one side, or you can bring it to one side, and then the only thing that's left on the other side is 0, that's homogeneous. If you ever have a situation where you have something on the right-hand side, which is just a function of the independent variable, which is here R, that's a non-homogeneous ODE or a non-homogeneous PDE. And in this case, it's still easy to solve. We can still separate it out. But there are, we'll get into later in the class solving non-homogeneous PDEs and ODEs. And there's more techniques that you can bring to bear on that situation. All right, so we'll just make a mental note that this is now a non-homogeneous ODE. Okay, but let's solve it by integrating. What do we do here? So let's, right? We can just take the dr, bring it over to the other side. We end up with d of r dt dr is equal to what, minus r g dot triple prime over k dr. Integrate both sides, and we then end up with. See, I'm going to move up here to the other side. R dt dr is equal to minus g dot triple prime times r squared over 2k plus our constant of integration, c1. Hopefully that's straightforward. Again, now we can bring this r over to the other side and dr over to the other side, integrate. We have dt is equal to, let's see where I lost my notes. All right, so dt is equal to minus g dot triple prime, or now r because we've brought r to the other side divided by r. So it's g dot triple prime r over 2k plus c1 over r times dr. Right? So just bringing the r stuff over, integrate both sides. And our solution ends up being t is equal to minus g dot triple prime r squared over 4k plus c1 ln of r plus c2. Okay, this is our general solution for temperature for this problem. And again, like I say, general solution. This does not yet apply any boundary conditions to the problem that we have. This is a general solution. And what does it include? It includes a situation where you have thermal generation, and it's a situation where you have a cylindrical geometry. Right? And in fact, if you look at this, it's actually, let's see, this part here is exactly the same as it was before. So what is that saying? I've added thermal generation to this. I still have the same solution I had without thermal generation, but I'm adding an extra term in there. So you're sort of laying this new solution on top of the old one, which is kind of an interesting thing, I guess, mathematically. All right, any questions on this, how we got this far? It's all just sort of calculus.